Good. We should be good to go. Thank you so much, David.
Yeah.
Bye. Okay, so my apologies for the people who are actually here. I'm going to recap the stuff that that I said at the start. We're just looking at Euler's method. Euler's method is like a linear approximation method. So it's what falls under the class of what's known as numerical methods. All right. We don't necessarily, so we're saying I don't necessarily have an analytic solution. I can't find a function that solves this differential equation. So I'm going to do something that allows me to just get myself an approximate value. All right. We should be quite clear. Newton's method is the basis for a lot of numerical methods. All right. So back in 70s and 80s, the tidal flows in Spencer Gulf were actually modeled. And they did this type of thing to model it. All right. So the methods they used were based on this type of system, right? Where what they knew is they knew about they measured tidal flows in certain spots. And then from that, and some just understanding the physics of that, they are able to do that. And what that did is it allowed them to show where the particular dead spots were. And that's actually where the fishery, that's where the nursery for like the prawn fishing is done. All right. So that's where the baby prawns are born. What they did is they then made that a marine park. They banned fishing in that region. And what that allowed the prawns to do is they hatch, they grow. When they're older, they move out, and that's when you can catch them. So the prawns, the adult prawns will go there to lay their eggs, and it's just because it has this particular property. And they're able to find that using a method like this. Quite a complex, it's seriously cool. The guy who did it, the lead guy, a guy by the name of John Noy, worked here at Adelaide, and he got invited to do that all over the world. So it's such a powerful method, and it's relatively simple in the concept. All right. So all we're doing is we're taking a point, we're taking a differential equation where we've got y as the derivative of y with respect to x as a function of both x and y. And this is based on this idea that I can do what's called a linear approximation. Something like f of x is approximately f of a plus f dashed of a by times x minus a. That gets me a straight line approximation through a. So when we're setting this up, I've chosen a differential equation. I'm going to choose some information. So I'm going to start at 1, 1. So x is going to be equal to 1, y is going to be equal to 1. I want to work out what the value of y is when x is equal to 2. This will only ever give me an approximate value. But if I put in these numbers into my differential equation, it's going to be like 2 times 1 plus 1 minus 1. And that's going to be equal to 2. All right. Forgot to do the thing where I go h is equal to the change in x divided by n, the number of steps. And so in this case, my x is going to change by 1, and my number of steps is going to be 2. So my h is going to be a half. So I'm going to do a half times by the derivative, 2. The advantage is, so the h is the change in the x. And by working out this, so this is always going to be sort of 1 plus h, 1.5. This is going to be 1 plus delta y, which is going to be 2. And so at each stage, I work out my new point. Then from my new point, I work out what the next derivative is going to be. So I'm going to do the same thing. It's going to be like 2 times 1.5 times by 2 plus 1.5 minus 2. That's going to be what? 3 times 2 is 6. So it's like 6 minus a half, which is equal to 5.5. Hopefully. Quick check. Did that make sense? Yeah. 2, 1.5, 2. Beautiful. Yes. Good. Okay. You notice I'm trying to check because the last thing I want to do is make a mistake while I'm doing this. And I'm prone to making mistakes. All right. My brain goes, that's the number, and my hand says, no, we don't want to write that number today. So we can, if I do something silly, let me know. Let me know. So this should get me 11 on 4. So my change, so in actual fact, this thing sort of went quite steep at the next point. Okay. And so but this is the value amount I change y. So my x is going to become 2, my y, so it's going to be 2 plus 11 on 4, which we might write as 19 on 4. All right, that's where it stopped. So this is as much as they would get you to do in an exam, okay? Typically, if you're doing this in an assignment, you would do 4 points, all right? Not too many, but not too much. Yes. So, yeah, so you can see up here, this is why I've done my change in y is the derivative times by the x step. All right, so if you think about the derivative, it's the slope, so that's a rise over run. If I times by a run, then I get the rise, the change in y. So this is the beauty of this method, right? We're going, this is the slope. I can go, all right, I want to work out how much I know how much my x value is going to change. If my slope is this, how much will my y change? And so we're able to go, oh, it's going to happen this way. And so just by plotting this out, I can get myself a curve, all right? I don't want to go through the whole process of working out what that's going to be. It's going to be tedious, but it will get me a function, all right? It will get me a line, and it will be, so the smaller the steps I make, the more accurate it will be, all right? Typically, if I'm doing this, Excel is great for doing creating a table. So you can see how you create all these things. And this one's a nice, easy, I'm just going to add H and fill down. This one, because it by creating this change in Y column, I'm allowed to go, oh, this value plus this value gives me the new value. And so it makes it easy to program into like an Excel spreadsheet. Okay. So what you need to do, so when you're thinking about what you have to do, all right, firstly, if they've said Euler's method, you will need to identify the f of x. Occasionally, not very often for exams, but occasionally they'll make you rewrite it so your equation fits this pattern, all right? So with differential equations, there's a, does it fit my pattern, all right? And so I'm going, all right, my derivative is equal to a function of x and y. Once it's in that form, I've got the thing that I can put down here, all right? This is just my f of x, y. There is nothing wrong with making, with the table. I pointed at a spot that's not on the screen. That would make a lot more sense. Anyway. So once we've got it in our differential equation form, we can create the table. Some people will do this slightly differently. Some people will do 3 columns. Some people will do a 5-column thing. Depends how you want to, depends what makes sense to you. We're focusing on this idea that with the differential equation, like if I know the derivative at a point, I can get a straight line approximation, which is what this thing is saying. So by setting it up, x value, y value, the derivative value at that point, all right? Because it's dependent on both x and y, it changes at any point in the near area. And so I want to then, once I've got my derivative, work out how big my y, how much my y is going to change. And so you see here, this was 1, this is like 2 3/4. So, yep. So you have to create the equation. So if they haven't given it to you in exact form, you need to make sure you've written out the equation like this. Oh, no. So if it said Euler's method, it means you have to do this table thing. All right. Now, you will not lose marks if you do the table differently from what they've said in the lecture. All right. If you've all the ways of constructing this, you need to have the value for the derivative. Whether you work out, whether you just go, that value times by the change of x is what I add here, or whether you create the table that gives you the change in y value. I like doing the change in y value, partly because I'm always teaching this. And so it makes it easier. It gives me that thing to talk about that says, you've got the h, which is your change in x. You've calculated this, the y, change in y. And so you can just add h, add change in y to get your new points. All right, and then you recalculate the derivative at the new point because the slope will have changed by then. All right, and obviously the smaller I make my steps, the more accurate my method is going to be. All right, so the better the approximation will be. Yeah, so it's a good question. You do need to, you do need to have it written in the right form. Once you've got it in the right form, you create the table. The table, there's nothing magical about the table. Not okay. But yeah, so yes, these are good things. As you go further on, there's whole courses. I did honors courses in numerical methods. They're really quite interesting, the ways we've gone about doing these things. But that's what we're doing. Do we have more questions? All right. You know what? We're going to go one. Okay. Okay. Equation of a plane. Now, the problem isn't so much equation of a plane. What we might do is I might stop sharing this one. And I might start to... there it is. All right. So, I have the right one. That's one outline. I'm just going to go that one. So part of this is just trying to work out what I want to do is I want to work out what you need to know. So if I look at page 99. What before that? So with equations of the plane, I don't know, you still haven't got there. This is one of those things where we're going to talk about what you need to have, right? So for the first thing to understand equation of a plane, okay? So what do you have to have for the equation of a plane? Two lines. All right. So if I were to have two lines, L1, which was equal to, I don't know, 0, 0, 1 plus t by 3, 2, 1. Make it nice and simple. And L2, which is going to go, I don't know, minus 1, 1, minus 1 plus t by. So I don't know, I don't know, we'll add some 1 minus 1, 1. That'll confuse people. Sure. Okay. So I need to make sure my lines are not parallel. Okay. Obviously, in an exam, we've gone to the trouble of not doing that, but it is actually worth saying. All right. So we need to have the thing that helps us define the plane. So two lines that are contained in the plane might be a thing. In this case, because I haven't run the numbers carefully, I am going to go, it may or may not work. But what I can do is I can get plane that will contain lines parallel to both of these. All right. So I'm going to go with this, going to work with it. So I can't guarantee I'm going to get the plane because I may have chosen lines that there's no plane that's covering it. So I'd need to sort of adjust the lines so that they had a point in common. Okay, let's do this. But I still haven't actually worked out, like, when you think of the equation of a plane, what does it look like to you? Are we thinking something like ax plus by plus cz is equal to some number? Yes. All right, so this is a standard like Cartesian form. All right, these would be vector forms of the line, of lines, but also they actually qualify as parametric forms. All right, strictly speaking, when we say parametric, we actually mean it would be like 3t, 2t, and t plus 1 would be the parametric form. Vector form, parametric form. But this is still, because it's dependent on that parameter t, makes it a parametric form. So we just choose to emphasize that it's the sum of vectors. Okay, I need to work out these numbers. All right. Now, the actual thing I want you to think of when you're thinking of doing the equation of a plane is the normal vector. All right, so first thing to do, all right, so the first thing we want to do is find our normal vector. We're going to call it n. And I know that n dot with x, y, z is equal to normal dot p. Right. P, a point on the plane. Okay, so in actual fact, why this works is that when I put that vector in, it's like doing the dot product of that vector. And so if it's another point on the plane, the bit parallel to the normal, bit perpendicular to the normal will give you 0. And so it should be equivalent, get the equivalent dot product. Quite often we write something which is like normal dot with x minus x naught, y minus y naught, z minus z naught. The reason I equal to 0, this is equivalent. All right, it's really important to say this is equivalent to this. All right, and so it's about which form works for you. I remember this form because it makes more sense to me. Okay, it's just a form that makes more sense to me. How am I going to find my normal vector? So made it clear that I need my normal vector. How do I find my normal vector? All right, I feel the correct answer. Yes. Cross product, awesome. So you notice I said I can't have vectors that are parallel. That is because when I do the cross product, that would give me the 0 vector. All right. So if you do the cross product of two vectors in the same direction, it will go, oh, that's terrible plan, Nick. I'm going to give you 0 because I can't do that. I haven't got enough information. So cross product, I'm sure if you talk to while the lecturer was talking about it, he would have said cross product is a very special thing and only exists in 3 dimensions. Okay, so we can't do cross product. There is a much funkier argument that says there are only actually 3 dimensions in which we can find a cross product that does this thing. And if you get David talking about it, I don't remember the details, but they can arise from extension of the numbers. So you know how we have complex numbers, all right? And another extension is the thing called the quaternions, from the quaternions, basically 4 things with like 3 versions of the complex number. The cross product arises from doing something like that. Okay, so my n is going to be equal to, and so we're going to do I, j, k, first vector. So the direction, we're interested in the direction. So this is point, this is direction. This is point, this is direction. So I'm going to go 3, 2, 1, 1, minus 1, 1. And so by expanding out the thing, I'm going to go I by the subdeterminant. Take out the row and the column. It's going to be 2, 1, minus 1, 1, minus j by, take out the row and the column. And so it's going to be 3, 1, 1, 1, plus k. So you notice when I'm expanding the determinant, alternating signs. And so 3, 2, 1, minus 1. Okay, this should be I times by 2 plus 1 minus j by 3 minus 1 plus k by minus 3 minus 2. It's going to be 3i minus 2j minus 5k, or the vector 3 minus 2 minus 5. Okay. So I've got that all on the page. So going to just do it. I'm going to assume that this point is my point. So my P is equal to 0, 0, 1. Going to make my life easy. So I'm going to do normal vector, 3 minus 2 minus 5, dot with x, y, z is equal to 3 minus 2 minus 5, dot with 0, 0, 1. Okay, so this is just going to be 3x minus 2y minus 5z is equal to 0 plus 0 minus 5 minus 5. And so this fits the form I've got up here of the equation of a plane. So we know we've done the right thing. All right. Now, yeah. So yeah, this is actually one of the things that people find hard. It's actually really good that you ask. So what we're asking is about how to identify the different parts of the vector, basically. All right. And so when you look at this line, so when I have the line in vector form, I will always have a bit where a point that the vector goes through plus t times the direction. So in a straight line, this is like your c, and this is like your x, and this is like your m. So the m is like the slope or the direction of the line. Okay. And so if we think about it in analogous terms, the problem with so in 2 dimensions, the c is the y-intercept. The problem with lines in 3 dimensions is they don't necessarily go through a point on any of the axes. I can't guarantee it's going to go through any axis value at all. I can tell you where it crosses, say, the plane x is equal to 0. All right, so that's going to be sort of the plane containing y and z. But that's not particularly helpful necessarily. I could rearrange my equation to make it more helpful, but I'm sort of forcing on a construct. All right. Whereas there could be lots of forms of this line. All right. So I can have any point that's on the line, and I could have because the direction is a direction, I'm not interested in the magnitude. I'm just interested in which way it's going. And so I could have a scalar multiple of this. This is one of the things where, when we're talking about vectors, where sometimes we're asking the role they play in the calculation we're doing. And this is saying, actually, the direction is just, I'm not interested in magnitude, so therefore I can actually change the magnitude by multiplying by a scalar. All right. And sometimes, like if I have, so one of the things that set me apart from other students is when I saw an equation like this, where that direction had a fraction in it, the first thing it is multiplied through to make it all integers, to make my life easier. I don't want my life to be hard. I want it to be easy. And so choosing to multiply by a constant to make them all integers, because I'm only interested in the direction. So you have to identify this is a direction. I only need to worry about that part of it. The actual magnitude is irrelevant. All right, that can reduce the complexity of the calculations you're doing. All right, so the thing is, almost never do we just go, we want to sort of find the equation of a plane. All right, we want to do more than that. Our favorite pastime might be to go, so this line, I'm going to say I'm pretty confident is parallel to this plane. All right, because I've chosen that direction to be in the plane, but I don't think this point is on the line. Well, we could check. We could actually do this. Is -1, 1, -1 on the plane? And all I do is just take these values. So I go 3 by -1, -2 by 1, minus 5 by -1 is going to become, so this is going to get me -3, -2, plus 5. Oh my gosh, check it. All right, that's going to be equal to That's going to be equal to 0. Did I do that right? Tick, 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 0. Okay, so that's equal to 0. It's not equal to -5. Not on my plane. That is a problem for me. Okay, so the point to ask is the point on the plane. I've just subbed those values in. All right. So how far away is the plane is that line from the plane? All right. So the question we want to go, we could think of the plane as, I don't know, my planet surface, and this thing is just above my planet surface. How far away is it, sort of thing. Okay. So that's like the next thing that we'd get asked. All right. So because the plane is going to be parallel to this direction, this line is parallel to the plane, I can choose any point. And so it makes sense to choose the simpler point. I'm just going to use this point, and we're going to go, how far away is that point? Now, what I'm going to do is going to sound really silly, all right? But the shortest distance will be the perpendicular distance, won't it? So I'm going to create a new line, which is going in the direction of the normal through this point. All right. So I'm going to go my line K is going to be equal to this point, -1, 1, -1, plus T by the direction of the normal, 3 minus 2 minus 5. Now, okay, I'm going to expand this out and write this as -1 plus 3t and minus 2t plus 1. If I was consistent, that would be really helpful. -1 minus 5t. Now, what I'm going to do by creating this line, if I then put this into the equation of the line like I did before, I'm going to solve for a value of t. All right. So let's do this. Let's go. All right, got my equation. So I'm going to go 3 lots of -1 plus 3t, minus 2 by minus 2t plus 1, minus 5 by -1 minus 5t. And I'm going to make that equal to -5. Okay, so -3 plus 9t plus 4t minus 2 plus 5 plus 25t. Sweet, is equal to -5. Now, so if we bring all the numbers, -3 minus 2 plus 5 plus 9t plus 4t plus 25t is going to be equal to -5. These conveniently cancel out. All right, we knew that was going to happen. All right, that point was part of what was happening here. And so this is going to get me, what's that? 13 plus 25 is 38. Sure, let's pretend. T is equal to 5, and so t is equal to -5 on 38. All right, some of you might be people like me who are terrible with remembering the minus signs. And so you notice I originally wrote 5 and I didn't, and then when I'm copying it down from above, I've actually just checked, I've actually done a bit of a scan up the page and gone, what was that value before? Oh, actually the line above it's a -5. I can look at it, and I've practiced so much now that I can look at it and go, oh, it should be -5, not 5. All right. Doing a little bit of self-checking, even just in your working, can help you spot an error sooner. Okay, so we've got this distance. And so that tells me that the point, I'm going to call it Q, which is on the plane, is going to be equal to -1 plus 3 by -5 on 38. -2 by -5 on 38 plus 1. These numbers suck. -1 -5 by -5 on 38. Okay, so that's my point wherever this is. I'm not sure I'm even going to try and simplify that for you. All right, so once I have the 2 points that I know form a perpendicular line, I can then go, what's the length of that line? In actual fact, so if I do, what did I call it? If I do q minus 1 minus 1, 1 minus 1 is equal to some r, then we can work out the length of r. I'm not going to do that because those numbers are going to suck. You know how to find. So you notice I'm forming, the r is the direction vector from my point to my point on the plane, to my point Q on the plane. And so then by asking the length of it, I find out how far away that line is from that plane. All right, that actually is kind of funky. I reckon we should do that in the exam next year. I'm going to make the jump. So I don't write we should be quite clear, I don't write the exams. I have written some exams, but yeah, slightly different take on it, slightly different version. So do we have more questions about doing that? All right.
Let's speak through the steps so you find this.
Okay, so what did we do? So I've been asked to talk about the steps I'd go through to do the equation of the plane. So first thing I did, let me say, all right, so I'm going to say directions in the plane. And what I mean by that is, with this case, I had straight lines. So if we were given, say, so because we're told in terms of lines, we could get the direction straight from the lines. If I was given 3 points, all right, then I do, like if I'm given my points PQR, typically our PQR, we do the PQ, the PR, and that gets me 2 directions. All right, so the first thing I do is identify my 2 directions. All right. So identify our 2 directions, second step, right, find the normal. Find the normal, so cross product. Yeah, well, you can use, so if you have 2 points, if you have your 3 points, you can create any 2. So you can do PQ and you can do QR, or, there is basically only, if you think about it, you've got PQ, PR, or QR as the 3 directions. I could swap those around and again, so PQ is the same as QP, except for it's in the opposite direction. And so, and that's one of those things, because it's the direction I'm interested in, I can times by a constant. And that means if I want, I can multiply by a negative number. Okay. So because I'm only interested, so I've said it's a direction that I'm interested in, I can deal with just the direction concept. So yeah. So I can make it length 1. I could make it, I can choose its length. For what I would do, I would choose values to make the numbers nice. All right. So if I, for example, to see if my one of my vectors was 2, 4, 6, I would probably take the direction 1, 2, 3, because they have that common factor, and that makes it it simplifies the calculation. Reducing the numbers simplifies it. or making them all whole numbers. So if I have, 2/3 and 1/3 and 7/3, times it through by 3, so I've got whole numbers, because it reduces the complexity of the thing I'm thinking about. All right, and it just makes it simpler to work with. So what was I finding the normal cross product of the two directions? Three. So at any one of these things, all right, at any one of these things, I have some choice, and there's different ways we can choose to tell you what that thing is. All right, so if I've got how I choose to, so one of the fun ones they love doing is giving you a line and a point that are in the same plane. All right, because if you use two lines, you have this problem that they may not, like I did, they're not in the same, they won't be contained in the same plane. Whereas if I do a point and a line, so then if I've got the point and the line, to get my two directions, I can use the direction of the line, but then I take any point and do any point Q and my point P and do a PQ. And that will be another direction, which is not the same as the direction of that line. And so think about it, I've got to find two direction vectors in my plane. So how I do that is kind of like a choice. Once I've found them, I do the cross product of those two things. And then it's just down to do the equation. So it's going to be n, my normal vector, dot with x, y, z. And you saw x, y, z, I just mean the variables x, y, z is equal to normal dot p. All right. And that gets me the equation of my plane. Yes. Yes. Sorry, that's that was for David David thought he made me host, but that's why we missed the first 10 minutes. Hopefully I've recapped the key points from that 10 minutes. So, okay, if you've got to go, yeah. So yes, this is actually a really good point. The recording for this will go up online. It will probably be up this afternoon. So if you look at the Maths Learning Centre website, there's a bit that says resources, and you find Maths 1A, Maths 1M, and then you can go. This one should come up. Hopefully, I've written down enough information that David can put a couple little bits in there to go. We talked about this bit, and then this bit, and then this bit, so you can actually. We try and break it in. We try and put markers in there so that you know what we're talking about at what time. What's that? No, this I think I don't know. We usually put the revision seminars up on the Maths Learning Centre's like private YouTube channel, and then we can just include the link. Not 100% sure where we sit with that now, but yeah, so I'm not sure if it's going up on Echo 360 but it will be available. It's usually you have to get behind. You have to be a University of Adelaide student to see it. All right. So yeah. Okay. I think I'm going to leave equations of planes there, equations of lines as well. So on the plane. So if you look back at what I was doing here, I took a line. So I've taken my vector form of my line and written it in what would be called parametric form. And then what I've done is I've substituted that point into the equation of the plane I have. And that's what I was doing here. So you can see I've taken this value, times it by 3, minus 2 times this one is that bit, minus 5 times that one is that bit, said it's equal to 5. Then I've expanded this out. Expanded it out. I've grouped all my numbers. My numbers conveniently worked out to be 0. Pretty happy about that. My t's, grouped all my t's, and I know it's got to be equal to -5. So to make it so that it's actually on the plane, that got to be equal to 5. So that got me my value of t. And so to get my point, my q, which is on my plane, but also on this line k, I've taken my value of t and substituted into the equation, the parametric form of the line, and that got me this thing here. And I mean, like, the reason I haven't done this is because this is going to be like -38 minus 15, which is going to be like -53, like -53 upon 38. And so these are not happy numbers. I don't know, that's like 10 on 38. Yeah, don't want to. So I can't, so once you've got that value of t, you can put it back into the parametric equation of the line, and we can get the actual value. All right. That's why I didn't go, I'm going to work that out, because it's going to be horrible numbers. Horrible numbers. Nobody wants that. Okay. And then we have sort of, these are the sort of, that sort of breaking it down. If I'm doing the equation of plane, I need to find my directions, because my directions are going to help me to find my normal. Once I've found my normal, I need to have a point. Once I've got normal and point, it's really a simpler matter of basically writing out the equation. Loving it? Sweet. Okay, so this sort of feeds in a little bit to the concept of parametric equations. So, and then there is a horrible thing. Parametric curves. Parametric curves can be difficult. Okay, so did you see the equation of ellipse? No, the last thing you say is, yes, I think I do believe it. So an equation of ellipse is nice because it's something like this. All right. Okay, so the equation of an ellipse looks something like this, which is awesome. When I want to parameterize this, all right, I'm going to exploit some, so I can see something in that straight away, right? That form says to me cos squared plus sine squared is equal to 1, all right? So that's my first thought when I do this. I go, okay, so I want to make it look like, I want it to look like cos squared theta plus sine squared theta is equal to 1. So that I'm actually going to write it as cos t all squared. I want to be equal to x squared on a squared. And so by rearranging that, I can go, well, okay, so a squared cos t squared is equal to x squared. Take the square root. Now, when I take the square root, I can choose the plus or minus. All right. So I can go, I'm going to write x is equal to a cos of t. Okay. I could have chosen the minus. No problem with that. But I don't generally go that way. That's sort of like, there may be a reason to do it, but equally, probably not. And so in the same way, I'm going to equate this bit to the y. So I'm going to go sine of t all squared is equal to y squared on b squared. It's going to cut to the chase and go b sine of t. And again, so I had to do a square root in there. I had that arbitrary choice about the plus or the minus. I need to be careful, right? Once I'm doing the second one, I might actually need to make sure I've actually chosen correctly, like a thing that matches the equation. The other one is, this was a bit of an arbitrary choice, whether I chose x to go with cosine or y to go with cosine. It's a choice. All right. So, but I sort of back check. I sort of go, hey, does it still work? All right. And so this is a way of describing what's going on. So I could describe a point on a point on the ellipse is going to be, so I can go A cosine of t, B sine of t. All right, and we kind of, so this actually defaults back to the concept of the equation of a line. All right, so, sorry, equation of a circle. Because an ellipse, a circle is just an ellipse where both those A and B are equal to 1. And this would be the point on a unit circle. So it gives me that we can see that it's going to work. And so this is just something that would, for a value of t, trot around the outside of my ellipse, map out the points on the outside on the ellipse. So so it can be really hard to pick a parameterization. All right, most of the things that's going to happen is that you're going to like you guys engineers. Yes, engineers or physicists, you're going to want to do this, all right? And so one of the great ones is you've got a surface. If I just sort of sketch myself, I'm going to try and, all right, so I might have something that sort of does, I might try and sort of create a path that goes around 3 points on the edge of, yes, good work, well done. You're all over this, nice. So I might be trying to sort of, I don't know what color that is. That one. I might be trying to sort of trace out this path. Okay. And so that might be, all right. So when I'm doing, if I want to find a path, a parametric path, all right. What I want to do is I want to work out my, so I don't know, let's pretend this is X and this is Y and this is Z. All right, so this is sort of akin to creating a path. And so path needs a direction. All right. And like I say, when you get to sort of second year stuff, you'll see the what you call it, see the what you so this, so we're just creating it. We need a path to have an orientation. All right, so I've chosen a particular orientation. There will be, when you're doing this for purposes of calculation, you will need to know the orientation that you need to choose. There can make a difference, but it's a bit like, your orientation is a bit like when we're doing an integral from like A to B, typically A is less than B, all right? My orientation, so if I have my orientation around the wrong way, if I have my, B less than A, then I kind of get a negative involved. And that's, so when I'm using these parameterizations at that next step for the next part of the calculation, if I've got my orientation the wrong way around, I kind of get a minus sign involved, and you kind of go, oh, okay, this number should have been positive, it's negative, let's fix that. And just go, hey, I made my thing the wrong way around. Let's try and do something quite simple. Let's choose a point. So because it's on the z-axis, x and y are both 0, and I'm going to go 3. I feel like this one is on the y-axis, and so I'm going to make it 2. And I don't know, that feels a bit further out, so I'm going to go 4, 0, 0. And so by choosing my points, all right, what I'm going to do is my parameterization is going to be sort of, I don't know, arbitrarily it would be like P plus T lots of PQ, and T is in the region 0 to 1. This is a nice, easy way to do something, okay? So we're always going to do something that looks like that. All right, so let's try to go from our Z to X. All right, so the P is going to be equal to 0, 0, 3. And the Q is going to be equal to 4, 0, 0. And so PQ, which is always calculated by doing Q minus P, is equal to Q, 4 minus 0, 0 minus 0, 0 minus 3. All right. And so the parameterization of that part would be, let's call it L1. L1 is going to be equal to, we should go, L1 is the line, and so it's going to go through 0, 0, 3 plus our parameter times the direction. Sweet. And so, just as a bit of a check, if t was equal to 0, that would be that. And so I'd be at that point. Sweet. If t is equal to 1, so I'm going to have this plus sort of that vector. And you can see the 3 and the 3 cancel out. And I'm going to be at that point. It's going to be my thing. And again, I can write it in parametric form. So 4t 0, 3 minus 3t. All right. Now, you notice I've specified that t lies between 0 and 1. All right. So I've specifically chosen the line so that I've created so that t goes between 0 and 1. Now, for whatever reason, I may want my t to go from 0 to 2. And so I would half that length. All right. Or I might be talking about a section of the line that is defined by these two, but is sort of further along. T goes from 3 to 7. It's going to depend on what we're doing. All right. So the next part about this is when we go the other way. All right. So when we've defined our curve in terms of a vector, in terms of parametric form. All right. And that's so these are the reason I've done these specifically is because they're ones that you may see. And I want you to be aware of them, but we may get something. I'm going to go, what can we do? So I usually have X, I don't know, and Y. Okay, I don't know. I don't play with parametric curves enough to know a good example off the top of my head. So that's why I'm going, ooh, maybe what we'll do is we'll go 2e to the t. All right. And maybe I'm going to just try y is equal to t plus 1. Okay. What's it? So what actually, if you go back to the parametric form like this thing here, so when I'm trying to do like integrals in sort of 5 dimensions, right? And so what we want to do is ideally what we do is we try to simplify, we reduce the dimension of it, right? And since I'm integrating along the line, that's really a one-dimensional integral. So what I've done by parameterizing that line, all right, it gives me the line that I integrate along. Now, I'm not going to try and that be y. So that's why we do it. All right. And so that equation in itself is enough for me to go, actually, I can just use that equation to do this thing. All right. So I'm going to replace everything in terms. So I've got, because what this is saying is my function, which is, I assume, defined in terms of x, y, z. I've now got, for that line, I've got something that relates x, y, and z to a t. And so I can actually write that function in terms of just t. All right. And that brings it, so the thing I'm integrating is just in terms of t. The integral is over this range of t. And so I can actually do that integration. All right. So it allows me to integrate on this thing here. But what I've done is I've sort of gone, I'm going to put my head in that space so that that's like an ordinary graph sort of thing. So just ordinary, here's like my x, my f is like my y, And so I don't want to go too much into that because that's the next step. And you won't be doing that until you've checked it. All right. The point about it is I want to go, these are common things to do with parametric curves. All right. Some of the constant so with sort of more difficult curves, all right, we're going to have more difficult parameterization, and there's more to do. And I don't want to go into that, but it's confusing.
Yeah, no, what I'm asking, so we'll be given what? We're given 3 points there and X. Or are they vectors of their lines, and then what are we trying to get back at our level?
If I was to try and set this up, and maybe do that first step, I would go, hey, I've got these 3 points. I want you to give parameterization for each of the lines that are joining two of those points. Parameterize. Parameterize.
What's that doing? Is that?
That is saying, so that's the fancy way to create a parametric equation that describes the slide.
Okay.
All right. Yes.
Wait.
Yeah.
So we're just giving points and then we're finding a line between.
Yep. Effectively in parametric form. All right.
Okay, cool. So
Yep.
from like, will we have to find equations?
Well, so for this example, you have to break it into different line segments. All right, because I can't do it all as one line. There is not a nice way to do that. There's a couple of other things that, no, when you get there, we're going to worry about that when we get there. This you would just go, hey, I'm going to create myself 3 lines. All right, and if I was putting it in the exam, I would be specific in saying you will need to create the equation of the 3 lines that join each pair of lines, so that it's clear what I'm asking you to do. All right. So the first is the lines. I didn't write it down. I'm hoping they're going with it. They're very good at that. He knows what he needs to do. Nice, but not easy. All right. So remember, we're trying to get you to demonstrate and understand how to do all the things we talked about before. So we're going to ask you questions which are going to push that understanding. So there we go. After every exam, I get people coming in and going, oh, they didn't show us how to do that. And the answer is no, we didn't show you how to do that. But we did give you all the tools to be able to pick it apart, work out what was required, and to do the thing that was required. Okay? And so that's one of those things. But if you see an exam question and you go, I don't know how to do this, don't go, I've not seen it. Because we put some effort in to find something you wouldn't have seen before. But we will go, okay, you have all the tools. We'll ask you to find the equations of the plane, and we've given you some abstract information. But from that information, you can get 2 lines, from those 2 lines, you get configurations, you've got the goal, you've got the point, something like that. All right. So think about the information you've got. Think about I'm asking you for a equation of the plane. I need to have given you the information to find the normal and point. How is that information done? If I'm asking you to find the slope for a parametric curve at a particular point, I have to give you the information. So I might have given you parametric. So if I'm talking about the slope, and that's one of those things, I may have done this too. I may have gone, oh, this is your equation. All right. So I've told you what X is in terms of T and Y is in terms of T. I'm going, what is like you could actually get an equation. So from doing that, I could relate X and Y, right? I could actually get something to relate X and Y. So I could rewrite this one to say that T is equal to Y minus 1. But this is here. So this is like X is equal to 2E, and then, all right, Y minus 1. All right, sure. That's a thing. Now, that's kind of the wrong way around for the way we like our functions, all right? That's kind of going, I don't really like it that way. Just feels wrong. So what I could do is I could then go, well, like ln of x is equal to ln of 2e to the y minus 1. For me to apply, so I've got a product in here, all right? And so I can write this as ln of 2 plus ln of e to the y minus 1. the ln and the e are now going to cancel each other out. So I've got like ln of 2 is equal to plus y minus 1. And so ln of z. So I've got my y here. I can actually write this as y is equal to x minus ln of 2 plus 1. Now, if I was doing this, right, if this was me, I would go, oh, I've got an ln minus an ln. I can write that as ln of x on 2 plus 1. And so now I've gotten a formula which has y as a function of x. All right. With parametric curves, the trick thing to be able to do that, so I've looked and said the easiest way for me to do this was to rewrite y and then put y in. So I've got t as equal to some function of y. Then I put that value of t into the x. All right. Didn't have any idea what this was going to look like before I did this. Going to go, oh, that's kind of nice. So the next thing we know, though, is, so if we're finding dy on dx, all right, I can do a trick where I can go, well, that's equal to dy on dt divided by dx on dt. That should work, shouldn't it? Okay, good. Now, so if I go back up here, this should be equal to 1. And dx on dt should be 2e to the t. So I can actually give my derivative as a function of t. Interestingly enough, this is not going to do what I really was hoping it would do. 2e to the y minus 1. That's a bit weird. But, so I've given my derivative of y with respect to x as a function of y. I could do that. Nothing wrong with that. It's not great, but nothing wrong with it. Or if I was to differentiate that, so if I do dy on dx, so that should be, so when I differentiate, so it's like, it's going to work out to be 1 on x. That's interesting. See how up here, I said x is equal to this, which is exactly that. This thing is actually equal to 1 on x. I love it when a plane comes together. All right, so I can actually, I know that I can do either way. All right, and it will get me, I know it will get me the same thing. For a brief second there, I was going, is that really going to work? But yes, it does. So when we're doing parameterization, so the other thing they're keen on doing is going, what value of t? All right. So if I were to say, it goes through a particular point, because I don't know a particular point on this curve, I'm not going to try to do that. But what I would do, so if I was go, I don't know, if we do find x when y is equal to 4. All right. So what I would do at that point in time is, well, if I've got y is equal to t plus 1, but that's equal to 4, then I can sort of go, well, that tells me that t is equal to 4 minus 1, which is equal to 3. And so then x is going to be equal to 2 times e to the power 3. And who knows what e to the power 3 is aside from e to the power 3. So I have the feeling e to the power 3 is near 20. I have a feeling. Don't know. Have a feeling. So what we may do is get you to go, hey, identify these points. Specifically, I may actually go, so because I don't think I've done it with this one because of the way this thing worked out as a function. I may actually go, hey, where are the turning points? Or where is the derivative not defined? All right. And so if you think about it, dy on dx equal to 0, that's actually saying that I want dy on dt equal to 0, but not dx on dt equal to 0. All right. I need to be specific, because if we go back up to this expression, if this is 0, I need this to be not 0. Otherwise, I've got a situation where my function is undefined. So, and this would be horizontal. And so I could have vertical. Oops. Okay. Vertical. And so that's when I want dx on dt to be equal to 0. So I'm not going across. And dy on dt not equal to 0. So I need vertical movement, but not horizontal movement. All right, and undefined. Dx on dt is equal to 0, and dy on dt is equal to 0. Okay, so with that parametric curve, right, we've got different things, and each one of these conditions allows me to work out a value of t, because we're used to, like, what we've done is we've taken x as a function of t, y as a function of t. I'm bringing it down to the derivative. This one equals 0, and this one not, or whatever. And so when when we get some sort of wonderful clarification of these things, sorry, my microphone has gone dead, so I'm just going to talk loud. So when we're asked, so if both of these things are 0, all right, your particle has stopped. All right. So you think about with parameterization, I'm describing my position as a function of time. Is a way to think about it. Not necessarily the only way, but a way to think about it. And so if I have both of my derivatives 0, I've stopped. If my vertical direction is 0, my horizontal direction is 0, I'm stopped. And so, but if the vertical one is not 0 and my horizontal one is, I'm going straight up. And correspondingly, if my vertical one is 0 and my horizontal one is not, every so often I go, did I get those the right way around? But yes, then I'm traveling horizontally. So the parameterization allows me to have curves which wouldn't be functions in our traditional sense. So remember that way back at the start, we talked about a function being something where for each x value, there is only one y value. But from creating a parametric curve, so my ellipse, I can now go, well, my ellipse for t from 0 to 2 pi, there is only one value of x each time, and there's only one value of y each time. But if I was to draw it, because it's an ellipse, I put in my vertical line crosses it 2 times, but they're at different, the t value is different for each of those 2 points. The x value is the same, but the t value is different. And that's a thing that allows us to work with these functions to do an integral around a circular path. So, okay, that's quite tricky. Sweet. Okay, more questions? Yep, good. This is where I'm going, okay. So on the list were complex numbers and de Moivre's theorems. or proof by induction? What are we feeling? Induction. All right, sweet. Here's something I prepared earlier. Let's see what I want. Oh, there it is. That's what I want. So what I actually did is I calculated, I photocopied the section of the textbook from when I was in high school. All right. So when we're doing induction, it follows a very set pattern. Okay. So what I want to do is I want to be clear about the statement of the thing that I'm trying to prove. All right. So if I'm clear about the statement of the thing I'm trying to prove, then it makes my life easier. So what we're going to do, this is sort of all talking about the idea. All right. Definition: sequence is a sequence is a function whose domain is the set of positive integers. Blah blah blah. So I can do this. And so my fancy summation gives me a series. We don't want to know about that. What we want to do. Where did it go? Let's do one of these ones. There we go. I want to flick back a little bit further on. So some of these things are, so the hardest ones are the ones that involve divisibility. Okay, let's go and do this. I put pen there. All right. So all right. So do we think we can do that? Focus a bit better. Maybe. Okay, so I'm going to do a thing which says proposition is a statement which has a true or false value. So the proposition is this thing, 2 to the power n plus 2, plus 3 to the power 3n is divisible by 5. And I'm going, I have no idea. All right, but that's my proposition. All right, so I am going to go, all right, well, P1. Now that would be 2 to the power 2 plus 3 to the power 3 is divisible by 5. Well, this number is 4 and this number is, sorry? Yes. Good. Because I was in my brain, I was going, hey, that doesn't work. 27, which is equal to 35. P1 is true. Okay. That's funky and weird. But who knew? I know. I was like, I have this terrible feeling about this one, but I did deliberately choose possibly one of the harder ones, because I thought, well, what the hell? So the plan is, right, at the moment in my head, I'm going, I have a vague idea what this is going to look like, but I don't know yet. All right. And so there are a couple of things I do to help myself, right? So the plan is we're going to assume it's true for PK. All right, so we're going to assume true for K. And so we're going to go, all right, 2 to the K plus 1, 2, 2 plus 3 to the 3K is divisible by 5. Okay, that means 2 to the K plus 2 plus 3 to the 3K is equal to 5 times some number, I'm going to call it M, for argument's sake here. All right, so divisible by 5 means that I can write it as 5 times an integer. And so I need to say M is in the set of integers. All right, that will only be a problem. There's kind of a little thing which is like, you need to be clear about where things are. And then the other thing that helps. Okay, so I've said what I want to show. Now I'm going, okay, well, let's take that. All right. So when I'm proving something, I don't want to sort of go high. I don't want to have an equal state. All right. I want to start with the thing that I'm trying to work with. I want to somehow bring in the thing that I've assumed. All right. And so I'm going to go, this is where I'm going. Oh, I don't know if this is going to work. So let's start with this thing here. This is 2 to the K plus 3. First thing I want to do is actually trying to put it into something that looks like this. All right. So I'm going to write this as 2 times 2 to the K plus 2 plus 27 times 3 to the 3K. All right. Okay. So I feel like that's good. Yeah. Oh. Yes, please tell me. Okay. What's that? Yeah, so if it's 3 times K plus 1, it's 3K plus 3. That's actually, that is, so that's okay. This 3 to the K, 3K plus 1, there's brackets around that. And so it's 3 to the 3K plus 3. That's actually, I mean, like, that's actually a worthwhile point, all right? Because, see, the thing is, right, I do this all the time. And so I know I can sort of look at it and I go, that. But you're in the same group as people who turn up in your class, and there will be lots of people who had that question. So it's really important that if you see something you didn't see how it happened, you ask the question, right? Being the person who's brave and asks the question is good, because it may only be 20% of the class didn't see that, but they're really appreciating it right now. Okay. So, so this is going to be a funky, all right? No, so because the K was K plus 1 plus 2, okay, so let's try this over here. So the 2 to the K plus 1 plus 2, see so my K plus 1 plus 2, this I've just grouped together to give me plus 3. Sweet. No, that's like I say, I cannot encourage you enough to ask questions. But I am about to do a dodge. All right, watch this. Nothing up the sleeve. So I've got 2 times 2 to the K plus 2. And so I'm going to add 25 times 2 to the k plus 2 plus 27 times 3 to the k, 3k. I added this, so I've got to take it away. Otherwise, I'm kind of not balanced anymore. All right. All right. So this is the thing that people often don't think to do. All right. I'm going to add some. So I added it here. I took it away here. I put it next to this because when I do this, right, this is like 2 to the k plus 2, and that's 2 and 25 plus 27 times 3 to the 3k minus 25 times 2 to the k plus 2. All right, this is 2 to the k plus 2 times by 27 plus 27 times by 3 to the 3k minus 25 times 2 to the k plus 2, which is equal to, these are both times by 27. I'm going to whack a 27 here, and I'm going to go 2 to the k plus 2 plus 3 to the 3k minus 25 times 2 to the k plus 2. Hang on, I said this was equal to 5 times some number m. This is 27 times 5 times some number m minus 25 times 2 to the k plus 2. But this has a factor of 5 and this has a factor of 5. So this is 5 by 27m minus 5 times 2 to the k plus 2. Now, this is a trick. All right? Because I've now shown it's 5 times an integer, I've actually shown it's divisible by 5. All right? Like I say, this is difficult because that little bit there is something you kind of have to have seen happen. Okay? You kind of have to have seen it happen. But I've got this, and so I can then go, hang on, therefore, the thing I started with is 2 to the k plus 3 plus 3 to the 3k plus 3 is divisible by 5. That's saying p of k plus 1 is true if pk is true. All right, where? There we go. Yes. All right, sorry for cramming that in the last corner. So I've shown it's true for 1. I've now shown that for a particular value of k plus 1 is true. So if k was 1, then I've effectively shown that k can be 2, and it will be true. So P2 is true. P1 is true, therefore P2 is true. But since P2 is true, P3 is true. Since P3 is true, P4 must be true. And that is the principle of mathematical induction. Everybody loves the domino analogy. If I can knock the first one over, and this bit is, they are set close enough together so that they will knock the next one over. All right. I sometimes try a bit of the initial case is I can start my engine, and the inductive step is if my engine is running, it will still run. All right. So it's like it will keep doing that cycle over and over again. And so we have shown that inductive step. All right. So what we need to do is we need to finish it. All right. And it's really important because I've taken marks off for students who've shown the inductive step and shown the initial case and left it and not said, hey, I've shown the thing that you asked me to do. You know, the QED. All right. So the proof is not finished until you say, I've done the thing that is asked. All right, that's that QED. So we go, so we go, since P1 is true, and if pk is true, then p of k plus 1 is true. Therefore, by principle of mathematical induction, Pn is true for all n greater than or equal to 1. All right. I need to finish that statement. All right. So because it is the finish, this is the QED, that which is to be demonstrated. Quod errata demonstratum, I think is the Latin. Not entirely sure I got that right. Literally that translates to that which is to be demonstrated. And so I need to say, I did the thing I was asked. All right. So it's not good enough to just go, I think I can see I've done it. Okay. Do we have questions about that? So roughly speaking, should pause for a second and go, sometimes with induction, there's what's called strong induction and weak induction. All right. And so that other form of induction is where I don't just use the one previous thing, I use all previous things. Okay. Or more than one previous thing. All right. So if I show the first case is true, then the second case is only true if the third case, I need the second and the first, so on and so forth. And so it's important to recognize where that is. So, so with some sequences, they depend on two previous terms. I need both of those previous terms to be true for that next one to be true. And so I can have that thing which is dependent on two previous steps or all of the previous steps. Need to be a little bit aware if it's not coming out. So stating clearly what you are doing is really important. Okay. So that's my proof by induction bit. The other one that's really difficult is inequalities, because quite often what you're doing is you're going to replace your n by 1. And it feels wrong, but n is greater than or equal to 1. So therefore, if I have n this side and n is greater than or equal to, if I have n squared, I can replace that by 1 squared or n, because I can n squared is n times n. If I replace one of them, I can say n squared is greater than n, because n for n greater than or equal to 0. 1, actually 0. But anyway, but I want to, so I do things which I'm using inequalities which are either obvious or I've stated in the wording of the problem, which is why I need to be clear about stating all the bits. All right. So proof by induction shouldn't take you a long time, except for it's a lot of you need to write out all the steps so it's clear. Okay. Okay. So there are various things here. So what's actually happened with this? So these are some questions someone sent through, and it sort of said, hey, Z1 is this, Z2 is this, Z3 is this. Which of the write the following in the form. All right. So when I see that and I do this, we're remembering that complex numbers are like vectors. So when I'm just adding them, all right, nice and easy. So I'm not going to worry about that. When I see something like this, all right, that means I'm going to go, all right, well, it's going to be like 5 plus 6i by minus I minus 1 by 4i. All right, so we're going to say that complex multiplication is commutative. I can swap the order in any way I like. Right, so I could choose to put my 4i in here. So I could go 5 plus 6i. And then this bit is going to be 4i times by minus I. So it's going to be minus 4i squared. And then minus 4i. Simplify that a little bit. 5 plus 6i. And the I squared, So remembering I squared is always equal to 1, minus 1. I squared equal to minus 1. Make sure you say the right words. And so my minus 4i squared is actually just 4. Minus 4i. And then I can do the expansion. So that would be equal to 5 times 4 is 20. I'm going to do 6i times minus 4i. So it's going to be minus 24i squared. And then that's going to be minus 20i and plus 24i. Again, that's going to get me 20 plus 24. Minus 20i plus 4i is going to be plus 4i. And so this is like 44 plus 4i. There really is only one trick, and that is your I squared becomes minus 1 for the multiplication. Now, polar form. Everybody loves polar form, right? Yeah, polar form is so incredibly useful. It's ridiculous. But if we go back and think about quadratics, we love quadratics because quadratics are nice, really pretty. But we have that general form, which is like ax squared plus bx plus c, right? And that's called general form. But then there's a factored form. You might go a by x minus b times x minus c, and that's a factored form. Now, the general form, you go, that constant term is the intercept. That a at the front tells me whether I open up or down. Doesn't really tell me what, doesn't even tell me if there are roots, really. All right. You can deduce it sometimes, but sometimes you have to go as far as using the discriminant from the quadratic formula to work out if you're going to get roots. All right. Whereas my factored form, if I've got a factored form, I definitely have roots. It's telling me those two roots right away. All right. And there's another form, which is that completed squared form, where you go like sum capital A by x minus b all squared plus h. And so that's actually giving you the b and h is your vertex. And so that's emphasizing the vertex. The reason I'm doing this, right, is to say the form tells me something straight away, but it doesn't tell me everything, all right? Oh, your battery is running low. Awesome. I'm going to have to finish soon because I didn't bring my charger. Sure. Okay, so that's awesome. But when we're trying to do the complex number stuff, there's two forms, that Cartesian form and that polar form. So this multiplication, this addition stuff, really, really simple in Cartesian form. All right, bit of work, really simple. But then we have some horrible things. And so like if you look further down on this page, these questions about sort of length and so forth, they're sort of, you know, same sort of problem. They're probably best done in Cartesian form. Except for when I'm doing powers, all right? When I'm doing multiplication, division, powers of complex numbers, that's when my polar form is the best form to do. All right. So if you remember De Moivre's theorem, I'm going to turn this. And I never remember how to spell De Moivre's. It's like de. So we're going z to the n is equal to, so we go r to the power n cis n theta. All right. Where z is equal to r cis theta. And that's a shorthand for saying r by cosine of theta plus I sine of theta. Now, so we've got this beautiful thing happening here. All right. Everybody love it. We're all going, yep, that's great, Nick. We can walk away from this. But so the thing that we can do, that De Moivre's theorem allows us to do, is allows us to do things like square roots or nth roots. So, or the other thing that we can do, have we ever done this? If we looked at z cubed, all right, that is going to be, well, r cubed, and then is this 3 theta, which will be, so if I take z is equal to cos theta plus I sine theta. So I've made r equal to 1. This thing here, so when my z cubed is going to be but that's going to be cos of 3 theta plus I sine of 3 theta. Now, I've deliberately done something a little bit unusual, but I can expand this out. I can go, this is going to be cosine theta cubed plus 3 I cosine squared theta times sine theta plus 3 I squared cosine of theta sine squared theta. I'm going to go I cubed sine cubed theta. All right, sure. That sort of thing. Now, so let's just simplify this a little bit. Cos of theta cubed. I'm going to pick out the real terms first. And so that's actually going to go minus 3 cos theta sine of theta squared plus I by. So this is an I, 3 cos squared theta sine theta minus sine cubed theta. All right, sure. Now, I can equate real and imaginary parts. So I can go cosine of 3 theta is equal to cos of theta so cubed plus 3 cosine of theta and then sine squared theta. I've actually got an identity for a triple angle formula. All right. I've gone, hey, I can do this. I can actually create a formula. Okay. So, and in the same way, I can go sine. Oh, it's about to go down. All right.